Okay, now that we know or we discussed already the concept behind a resonance in series and also in parallel circuits. Now, in this lecture we'll be doing examples under series resonances, also under the parallel resonance. So first, example 5.11. So this is under chapter 5 of our syllabus. What inductance is required in series with a 30 microfarad capacitor with a resonant frequency of 8 kilohertz? So this is a series problem because we want to determine the inductance that should be connected to a capacitor which is 30 microfarad. So we take note that these two components here, the inductance and the capacitors, these are lossless or loss-free component. When we say loss-free component, it means there's no resistance of the two, or in other words, they are ideal components. So if you remember, we already derived the formula for this in a series RLC circuit. We already derived the formula for a frequency in resonance, and we call that f of r, and f of r is just equal to 1 over 2 pi the square root of L times C. So this is true if the circuit is a series RLC circuit, or if it's the resistance here is 0, it doesn't matter. Why? Because in our formula, we only look at the the L and C values when we are solving for the resonant frequency. So we're given with the resonant frequency, which is 8 kilohertz. So this is 8,000 hertz, and this is equal to 1 all over 2 pi times our L is the unknown. That's what we want to solve. And we also given with a 30 microfarad capacitor. So L times 30 times 10 to the negative 6. And the required inductance now, if you solve this, you can square both sides of the equation so that we have L will be equal to 1 all over 2 pi times 8,000. So this is squared. Then you multiply that with uh, 30. So times 30 times 10 to the negative 6. And that will be 1.319 times 10 to the negative 5, or in terms of micro. So 13.19. 13.19. So this is 13.19. The unit is micro, where the Henry, because this is the inductance L. So the inductance required in series with a 30 microfarad capacitor, so that the resonant frequency is 8 kilohertz, should be 13.19. Next, in a series RLC circuit, so solution. In a series RLC circuit with R equals 10 ohms, with variable frequency source, and L equals zero point 0.1 Henry and C equals 10 microfarad. So determine the impedance at a frequency 10 hertz above the resonant frequency and 10 hertz below the resonant frequency. So we want to determine the impedance, and when we say impedance is just equal to, so the magnitude of the impedance is just equal to the square root of r squared plus x squared. But x here, this is the difference between L and xc. XL is the inductive reactance and XC is the capacitive reactance. So we do that for a 10 hertz above the resonant frequency and 10 hertz below the resonant frequency. And the formula for X in terms of L is just equal to 2 pi F times the inductance. For XC is just 1 over 2 pi F times C. So before we can solve that impedance, we need to know what's our resonant frequency. So from our formula, again, this is an RLC circuit, so we can use our formula from this previous example. F of R is just equal to 1 all over 2 pi times the square root of L times C. And we already know L. L is the C equal to 0.1 Henry and C is equal to 10 microfarad. So this will be 1 over 2 pi times the square root of L, 0.1, times the capacitance, 10 times 10 to the negative 6 microfarad. And calculate that. Our resonant frequency will be equal to, so 1 over 2 pi the square root of 0.1 times 10 exponent negative 6. So the resonant frequency is 159 hertz. So this is 159.155 hertz. And of course, even the problem does not ask for the impedance at the resonant frequency. We already know what's the impedance at resonant frequency. Why? Because at resonance, the circuit becomes pure resistive. So it's just equal to 10 ohms. The impedance is just equal to 10 ohms. So we don't need to solve that. We only want to solve the impedance at 10 hertz above and 10 hertz below the the resonant frequency. So this is our resonant frequency. So first, at the first one, 10 hertz above f of r. So what will be the frequency? The frequency will be equal to 159.155 plus 10. So this will be equal to 169.155 hertz. And to solve for z will be equal to, again, the square root of r squared plus x squared. But first, we need to solve for x, where x is equal to the difference between XL and XC. So we need to solve for XL and XC first. So XL will be equal to 2 pi times this one, the frequency, 169.155 hertz, multiplied by the inductance, which is equal to 0.1 Henry. So XL will be equal to 106.283 ohms. And for XC, so this will be 1 over 2 pi of 169.55 times the capacitance, which is 10 times 10 to the negative 6. So the frequency will be equal to 1 over 2 pi times 1699.155. There should be 155. Then multiplied by the capacitance, 10 times 10 to the negative 6. The answer is 9 point, or this is 169. 94.08. 94.088. 94.088 ohms. So that the impedance 10 hertz above the resonant frequency will be equal to the square root of r squared. Our r is given, that's 10 ohms. 10 squared plus the difference, XL minus XC. So 106.283 minus 94.088 squared. So Z now will be equal to 174 ohms. C is equal to 100.74 ohms. This is the impedance at 10 hertz above the frequency. And at 10 hertz below the frequency. So at 10 hertz below the frequency, resonant frequency, below F, or our F will be equal to 159.155 minus 10 instead of class. So this will be 149.155 hertz. And we repeat the process. We solve for XL. XL will be 2 pi 149.155 times 0.1. And this will be equal to, so 2 pi times 149.155 times 0.1. 93.717. So 93.717 ohms. And for XC, so we have 1 over 2 pi times the frequency 149.155 times the capacitance, which is equal to 10 times 10 to the negative 6. 10 times 10 to the negative 6. And that is equal to 1 over 2 shape pi times point times 10 raised to negative 6. The answer is 106.704. 106.704 ohms. So that our impedance now at 10 hertz below the resonant frequency will be equal to R squared, 10 squared, plus the difference. So 93.717 minus 106.704 squared. So our Z will be equal to the square root of 10 squared plus 93.717 minus 106.704, and you still need to square that. That is equal to 16. Is this correct? 16.39 ohms. 0.39 ohms. I have a correction with the first impedance here. If I do the calculation again, square root of 10 squared plus 106.283 minus 94.088. Square that, this should be equal to 15.77. So this should be 15.77, not 100 something. 15.77 ohms. So this is the impedance when the frequency is above the resonant frequency by 10 hertz. It's 15.77, and if it's below 10 hertz, then it should be equal to 16.39 ohms. Okay, so next, still under series. A capacitor is in series with the coil with resistance of 40 ohms and inductance of 0.75 Henry. If the resonant frequency, there should be capital H, it's Henry. If the resonant frequency of the circuit is 55 hertz, determine the capacitance of the capacitor, the current, the power consumed, and the voltage across the coil. So we have an RLC circuit again, RLC, with resistance of 40 ohms. We have 0.75 Henry inductance, and we don't know C. You want to determine that the value for the capacitance. What we know is the resonant frequency, F or, which is equal to 55 hertz. And from this, we know the formula because this is again RLC. It's just 1 over 2 pi the square root of L times C. So we can solve for the capacitance here. So C will be equal to 1 over 55 times 2 times pi, and you square that. So 2 times 55 times pi, and we square this one, and you multiply it with the inductance, which is equal to 0.75 Henry. So the capacitance will be equal to, okay, 1 over 2 times 55 pi squared times 0.75. That is equal to 11.16. So 11 point, or yeah, 11.16 microfarad. So the capacitance is 11.165. 11.165 microfarad. And we also want to determine the current. The current is the maximum here. This is the current during the resonant frequency or in resonant phenomenon. So the current will be just equal to, because remember, when we are in resonance, these two will cancel out. It will be equal to 0. The circuit will be a pure resistive circuit. Okay, but there's something missing to the problem. There's no given source voltage in the problem. It says find the current, but it has no power source or voltage. So let's just assume a voltage given. Let's continue this one with a 200. So you just connect it here with a voltage equal to 250 volts. 250 volts. So what will be the current? So the current will be just equal to, because this will become a short circuit, because this will become a pure resistive circuit. So the voltage across the resistor will just be equal to 250, and you divide that with the resistance R, and the resistance R is just equal to, or is given, 40 ohms. This is at 55 hertz. So R is equal to 40 ohms. So therefore, the current will be equal to 250 divided by 40. So 250 divided by 40 using Ohm's law. And that's just equal to 6.25 amps. And this is actually the maximum current in the circuit when you're varying the frequency of the source. Next, and what should be the power being consumed? So this is just a real power. So we already know what's the formula for real power. The real power is the power being consumed by the resistor itself. And we already know you can use this current, or you can also use the 250 voltage as your formula, because the voltage across 40 ohms is just also 250. Or we can just use this current here, 6.25, you square that, you multiply it with the resistance, or 40, and that will be our real power, the power being dissipated by the resistor 40 ohms. So 6.25 squared times 40. And this is 1562.5. Unit is watts. And lastly, what should be the voltage across the coil? So what will be the voltage across the coil? When we see coil, the coil is not just the inductor. The coil is composed of, so this is the coil composed of the resistance and the inductance. So what's the voltage at this point here? And it should be clear. We should know the voltage at this point. We can just use Kirchhoff's voltage law. And we already know the current passing through here, I, which is equal to 66.25 amps. And if we consider the phasor, the angle of 6.25 amps, because this is pure resistive, so we know the power factor is equal to 1. So if the power factor is equal to 1, then therefore the voltage and the current is in phase. So if we make 250 our, the voltage 250 our reference, then the angle of I should be equal to 0. So if we add the voltage drop here and the voltage drop at the inductor, then that will be the voltage across the coil. And by Ohm's law, so this will be equal to 6.25. The current flowing, you just multiply it with 40. It's the resistance R. Then we just need to add. So this angle here, these are just zero angle. But we do this one in phasor or vectorially. Then next is, again, multiply 6.25 and the angle is 0. That's the current flowing through the X. X here, 0.75. So what will be XL? XL will be equal to 2 pi times F, which is 55, times the inductance 0.75 Henry. So VL will be, or XL will be equal to 2 ship pi times 55 times 0.75. That's equal to 259.181. 259.181 ohms. But this is a pure inductive. XL is just inductor. And it's just J. You need to put J there so that it will become a vector. So this, you multiply that with this current. So J 259.181 ohms. So what will be the voltage now of the coil? This voltage here. So we need to go to complex mode. So mode complex. And we have 6.25 times 40 plus 6.25 angle 0. Then you multiply this with 259.181 I. And this is equal to 1600 1639.06 volts. So 1000.059 volts. So what can we observe here? If you look at the result that we got, the voltage across the coil is much greater than the voltage source. So this is a special case, especially in resonance. This happens when we are in resonance or in an RLC circuit. It's possible, unlike in DC circuit, that the voltage source will always be greater than the load, the voltage of the load. But in this case now here, there's a possibility that the load voltage at the load will be much greater than the source. This is only possible in AC circuits because we have frequency. That's the cost of the frequency. And later on in your transformer machines and even in transmission lines, you will also found out some cases that the sending voltage or the supply voltage is lesser than the voltage at the load. So it's possible to happen. Okay, so this is sample 5.1.3. Then for the last example, for the series circuit, a loss-free capacitor is connected in series with a 10 millihenry coil to a variable frequency of 20 volts. The current in the circuit has a maximum value of 0.2 ohms at a frequency of 100 kilohertz. Calculate the capacitance of the capacitor, the quality factor of the coil, and also the half power frequency and the bandwidth, and also the bandwidth of the circuit. Bandwidth of the circuit is just equal to the difference between the half power frequency. So solution. So we start with, this is an RLC circuit again, and we have a current which is maximum at zero point 0.2 ohms when the frequency is equal to 100 kilohertz. So this means that FR is just equal to 100 kilohertz because the current becomes maximum when that is the case. So I maximum is equal to 0.2, and this is possible when we are in resonance. So if we are in resonance, just like what I'd said before, the circuit acts like a pure resistive circuit. The reactive component of the power will become zero. So in that case, if this is a loss-free capacitor is connected with a coil, a 10 millihenry coil with variable frequency of 20 volts. So now there's a tricky part here. We have a voltage or current zero point 0.2 ohms, and we have a coil, and the problem says it's a 10 millihenry coil. It does not say it does not specify the resistance of the coil. So remember, a coil is a combination of resistance and inductance, unless it is stated in the problem that it's a ideal coil, then the resistance is negligible. But in this case, the problem does not say that it's an ideal coil, but it says it's a loss-free capacitor, so it's an ideal capacitor. And if it's not ideal, then therefore there's a resistance on the coil. And this resistance can be solved. Why? Because we know the current flowing through the circuit. The current flowing through the circuit is 0.2 amps. So we can solve for R. How? Because we know that the impedance of the circuit, the total impedance, will be just equal to R. Why? Because we are in resonance. So this will become, it acts like a short circuit here. And we have a voltage of 20 volts. So from that, we can use Ohm's law. The current now, which is 0.2, is just equal to the voltage, which is 20 volts, divided by the resistance R. So if we solve for R, that will be 20 all over 0.2. So 20 over 0.2, and that is equal to 100 ohms. So the resistance of the coil is 100 ohms. So it's not a lossless coil because it has a resistance, and that is just equal to 100 ohms. Now, next, we can solve for the resonant frequency, or I mean the quality factor, because we know the resonant frequency. And what is the formula for our quality factor? Or before we can solve for the quality factor, we don't know the capacitance of the capacitor. That's the problem. That's the first problem, actually. We first need to solve for the capacitance by using the formula for the resonant frequency, which is 1 over 2 pi the square root of L times C. This is still valid because this is just an RLC circuit. And we know F of R, we know L, we can solve for C. So C now, the capacitance now will be equal to 1 all over, you square both sides, and this will be 2 pi times FR. FR is 100 times 10 to 3, that's kilohertz. You square that, then you multiply it with the inductance, which is equal to 0.2 10 millihenry, or that is 0.01 Henry. And you solve that. So this will be, so we have 1, 2 pi times the frequency. You square this and you multiply it with the capacitance, 0, or millihenry, or Henry, 0.01. Then we have the capacitance, which is equal to 253. We can turn that into negative 12. That's picofarad. So C will be 253.3. 253.3 picofarad. So C is equal to 253.3 times 10 to the negative 12, or simply picofarad. That's the value of the capacitance of the capacitor. Okay, next, how about the quality factor now? How do we solve for the quality factor? What's the definition of a quality factor? It's just equal to the energy, 2 pi times the energy of being transferred and consumed divided by the energy consumed. Or we can just use the formula directly. The formula says it's just equal to uh, XL divided by R, because we're solving for the quality factor of the coil. So Q factor is just equal to XL all over R. And what is XL? XL is just equal to 2 pi times the frequency. And that's frequency is 100 kilohertz. So 100 kilohertz times what's the inductance? And that is 10 millihenry. So 100 times 10 to the 3, then 0.01. That's XL all over R, where R is just equal to 100 ohms. So therefore, the Q factor will be equal to ship by times 100 kilohertz times 0.01 divided by 100. The answer is 20 pi, or 62.83. 62.83. And there's no unit for a Q factor. This is dimensionless, because the unit for X is ohms, the unit for R is also ohms. So that's the Q factor. Next, how about the half power frequencies? F upper and F lower. So how do you solve for the upper and the lower? We already derived the formula for that. We can review the formula. And the formula will be just equal to F lower is just equal to the resonant frequency. You can substitute the resonant frequency from the formula, and you subtract the distance between the two. That's R over 4 pi L. 4 pi times L. And F of R, we already know that. That's 100 kilohertz. 100 times 10 to the 3 minus R is 100 ohms, all over 4 pi times 0.01. So what will be the lower cutoff frequency? That will be equal to 100 exponent 3 minus 100 divided by 4 times pi times L, 0.01. The answer is 99.2 kilohertz, 99.204 kilohertz. 99.204 kilohertz. So this is the lower cutoff frequency. For the other one, the upper cutoff frequency, we can just add it. F or will be plus or 4 pi L. This is again 100 times 10 to the 3 plus 100 over 4 pi 0 0.01. So the upper cutoff frequency will be equal to, so we can just change this and make it plus. That is 100.796. 100.796 kilohertz. And for the last one, for the bandwidth, in terms of the frequency, instead of the natural frequency or uh, region frequency, angular frequency, we can solve for the bandwidth. We can use the formula R over 2 pi L, or we can simply use the formula also, the upper minus the lower cutoff frequency. So this is just equal to F U minus F of L. And 100.796 minus 99.204. So the bandwidth in terms of the frequency will be equal to 100.796 minus 99.204 will be equal to 1.592 kilohertz. So that's how we solve for the bandwidth in terms of the frequency. But if you want the bandwidth in terms of the without the unit hertz, then you can use omega. You just need to divide that with 2 pi. Okay, so that is the series resonance. And for the parallel, we have 3 again. You can solve this. Example 5.2.1. Determine the resonant frequency of a circuit with the coil parallel with the capacitor. The resistance of the coil is 5 ohms and the inductance 10 ohms. While the series resistance of the capacitor is 2 ohms and the capacitance is 40 microfarad. So this is a parallel circuit with a capacitor that has a series resistance in parallel with an inductor or a coil. So this is for the inductance. This is 5 ohms for the or for the capacitor. It should be, this is 5 ohms for the capacitor. That's 2 ohms. The C, the capacitance of the capacitor, I don't see any C. It's 40 microfarad. 40 microfarad. And for the inductance, that is 10 millihenry. So what do we want to determine? We want to determine the resonant frequency. And we already derived the formula for this type of circuit. So remember last meeting, last discussion, it's a parallel combination of two non-ideal capacitor and inductor. And the formula was just equal to 1 over 2 pi the square root of LC. You multiply this with R of C times or R of C, the resistance of the capacitor. You can check that in our discussion is 1. So RL squared times C. RL squared times the capacitance minus L all over, you just interchange this 2. This will become RC squared and multiplied with L minus L. And plug in all the values so that we can solve for the resonant frequency. So 1 over 2 pi times the square root of L is 10 millihenry. 10 times 10 to the negative 3 multiplied by 40 times 10 to the negative 6. And again, this is RL, the resistance of the inductance, 5 squared times the capacitance, 40 times 10 to the negative 6 minus the inductance, 10 times 10 to the negative 3 millihenry. All over RC is 2 ohms. multiplied by L. It's 10 times 10 to the negative 3. Then minus 10 times 10 to the negative 3. And the answer for this one should be equal to, so the resonant frequency is just equal to 397.9, or no, it should be 241 hertz. It's 241 hertz. 241 hertz. Next, a loss-free 5 microfarad capacitor is connected across a 25 ohm 0.5 Henry coil. So across means they are connected in parallel. Determine the resonant frequency of the parallel combination, the total impedance of the circuit at resonance, bandwidth, and Q factor. Bandwidth and Q factor. So let's draw first the problem. So we have a loss-free capacitor connected across, so in parallel. So the capacitor is loss-free, so it has no series resistance, and it's connected across a coil that has a resistance and an inductance. The resistance is 25 ohm, while the inductance is 0.5 Henry, and the capacitor is 5 microfarad. It's 5 microfarad. Now we want to determine the resonant frequency. This circuit is actually similar with our also discussion, previous discussion here. Somewhere here, this one, a coil and an ideal capacitor. So we already know that the formula for the frequency is different compared to that of the first one. So you can just copy that, put it here. And we can again substitute the values. So we have 1 over 2 pi, the square root of 1 over L times C. L is 0.5 times the capacitance, 5 microfarad times 10 to the negative 6. Then minus R squared, so 25 squared all over the inductance, 0.5 squared. And that will be our resonant frequency. And the resonant frequency will be equal to 100.34 hertz. You can check these answers. I'm not 100% with these answers. My calculator sometimes gives me different answers. It depends on the mode. And next, that's the F, or we want also to solve for the total impedance. So what will be the total impedance? Z. Impedance of the circuit at resonance. I can just put the solution here. Z will not just be equal to 25 ohms, but we can derive that. But the formula will be just equal to the inductance divided by, so this is just L all over R times C, where L is equal to 0.5, and we have R that is equal to 25 multiplied by the capacitance 5 times 10 to the negative 6 micro. So the impedance now, total impedance, will be just equal to 4,000 hertz, or 4,000 ohms. And for the bandwidth and the Q factor, uh, you can repeat the process as we did here. It's the same thing. And to solve that bandwidth, instead of solving for the upper and the lower, we can just directly solve it by using these formulas at this R over 4 pi L and R over 4 pi L here. So if we add that, that is just equal to twice, and 2 over 4 is just 1/2. So R over 2 pi L. And that will be the formula for the bandwidth, that is equal to R over 2 pi times L. R is 25 all over 2 pi times the inductance, which is equal to 0.5. And the bandwidth now will be equal to around 7.958 hertz in terms of the frequency. And lastly, for the Q factor. So the Q factor. What's the formula for the Q factor? For this type of circuit, it's just equal to X over the XL over R, or XL is 2 pi times F, which is 100.34. You multiply that with L, which is 0.5 Henry, all over the resistance 25. So the Q factor from this one will be just equal to 12.61. So that's the Q factor. You can use other formulas. You can substitute. You can derive the formula in terms of L and C only by using the formula of F of R, which is this, and solve for the Q factor. Okay. Now for the last example, I will just give you this one, this case, and you can solve this already on your own. This is a series parallel problem. It has a loss-free 1 farad capacitor connected across in series, or in parallel with the 1 ohm resistor, and then it's in series with the coil. So we have a coil and we have the parallel combination of the resistance and the lossless capacitor. Also, the inductor is lossless. So if you have here a circuit like this one, so what will be the problem is determine the resonant frequency of the system. So you can derive the resonant frequency of this type of system. And I can just give you the formula here, or the answer for the resonant frequency, and you can derive it on your own. And this should be equal to 0.4775 hertz. You can derive this. You practice to derive this one. This is the circuit. You just do the same thing, just like what we did in our discussion. And then after deriving f of r, you have a formula for f of r. In this type of circuit, you can substitute the values of the given and solve for the actual value of the resonant frequency. And it should be equal to this, 0.4775 hertz. Okay, so this is our last discussion under chapter 5 and our EE 124.